Hello everyone, and in this video, we're going to be taking a look at a concept that can make an IMO problem fairly straightforward. And this concept is called complex numbers. So what are complex numbers? Well, we're going to first define the unit I as a one number or one of two numbers, such that I and negative I are the roots of the quadratic equation x squared plus 1 equals 0, or x squared equals negative 1. But you might ask, squares are always positive. And that is true if x is restricted to a real number. But now we can define this imaginary number, I, such that x squared equals negative 1. And how does this help, you may ask? Well, it turns out that you can label things like the imaginary axis and the real axis. If you have a number a plus b times I, where I is that square root of negative 1 that we defined, and a and b are real numbers, then we can actually graph it as if it were a coordinate plane. So we go here, and then here. This ends up being a, and this ends up being b, then this ends up being a plus b times I. A natural question to ask is, well, what is this distance here? Well, it is obviously a squared plus b squared. And I'll just go ahead and call this z to make things easier. But how can we express this value here purely in terms of z? Well, in order to do that, we needed to find something called the conjugate. The z conjugate is equal to a minus b times I. So it'd go all the way down here. So that's a minus bi. Think of it as reflection across the real axis. Then this value a squared plus b squared turns out to equal a plus bi times a minus bi. If you're not convinced, then you can just expand this thing out, and this ends up being z times z conjugate. And we denote this thing here as the absolute value of z squared. It's also called the magnitude or modulus. I'll just call it the magnitude. So magnitude z squared is equal to z times z conjugate. And that's the main formula. And now things get really interesting if we consider the magnitude of z to equal 1. The set of all points such that the magnitude of z is equal to 1 obviously ends up being a circle centered at the origin of radius 1. And this is called the unit circle, so this has length 1. And if there's a point z on it, then z times z conjugate is equal to 1. So z conjugate is 1 over z. Alright. So what makes this different than normal coordinates, you may ask? Well, the thing is, complex numbers can be multiplied. So if we have a number a and then a number b here, then you can actually multiply the numbers. And then a times b end up being like all the way here, ab. Think of it as like, and it turns out that the product ab is just, you take a, you rotate it by this many degrees. Like if this angle here is theta, then you take a, rotate it theta degrees, and then take a homosity centered at the origin of scale equal to the magnitude of b. So, and the fact that complex numbers equals rotation is a fun fact called Euler's formula. It requires calculus to prove, but essentially states that e to the I times power of theta is equal to cosine of theta plus I times sine of theta. And if we multiply two complex numbers, then every complex number can be expressed as r times e to the I theta, and then that means that the magnitude of z equals r. Then if we have r1 e to the I theta 1, that's a, and then b is equal to r2 e to the I theta 2, then that means that AB is equal to R1, R2, which corresponds to harmosity, times e to the I times theta 1 plus theta 2, which corresponds to our rotation. So that's what's special about complex numbers and how they can be rotated. And now let's go ahead and go back to our unit circle, and we can do a lot of nice things with this. So we have, suppose we have a triangle ABC inscribed in the unit circle. Then we draw this, this, and this. And then we have the complex axis here. This is real axis and the imaginary axis. So now we can associate each point with a complex number. So that's A, that's B, and that's C. And a natural question to ask is, well, where can we find points like the circumcenter of ABC, the orthocenter of ABC, and so on and so forth? Well, the circumcenter of ABC is obviously, so I'm going to label points on the side here. A is A, B is B, C is C. The circumcenter O is just a point 0. And now the next question is, well, what is the orthocenter? Where is the orthocenter? And in order to do that, we need to construct the points diametrically opposite. So if this ends up being A prime, and so same for B and C, then A prime is equal to negative A because it's reflecting across the origin. B prime is equal to negative B, and C prime is equal to negative C. So this ends up being negative A. And if this is the orthocenter here, H, then recall from a previous video that I made that BHCA prime is a parallelogram, and hence the sum of the opposite two coordinates must be equal. And this means that H is equal to A plus B plus C, which is really nice, which is why we use ABC as a unit circle mostly. So that's the orthocenter. And now we're going to start discussing the feet of the altitude. That's the last concept we'll need in order to solve the IMO problem. So if we have the feet of the altitude here, if suppose you have points B and C on the unit circle, so that, sorry if that's a bad circle, that's B and C, and then we have a point P here. And we want to find out what the foot of the altitude D from P to BC is. Well, it turns out that D is equal to B plus 1 half times B, so 1 half times B plus C plus P minus BC times P conjugate. So how can we go about proving this? In order to do so, we're going to actually prove that the reflection of P across D ends up being, if we have a point P prime here, then P prime is equal to B plus C minus BC P conjugate. And in order to prove that it's the reflection, we need to show that BP is equal to BP prime. Because this expression is symmetric in B and C, so if BP equals BP prime, then CP also equals CP prime. So the goal is to prove that BP is equal to BP prime given these complex numbers. Well, the length BP is just magnitude B minus P, and the length of BP prime is just C minus BP prime, or it should be BCP prime. We want to show that these two are equal. Well, because the magnitudes end up being multiplicative by Euler's formula, we can take out the c from both sides, and then we have 1 minus bp conjugate. But the magnitude of c is just 1, so that ends up being this. B minus p, the magnitude, we need to show that it's equal to this. So how can we go about doing this? Well, in order to do so, we're going to multiply both sides by the magnitude of, we're going to note that the magnitude of b conjugate is equal to 1. So this, we can just put that on this side here. So we then have b minus p magnitude is equal to b magnitude minus conjugate, minus b conjugate times b p conjugate. So, and this simplifies down to b minus p is equal to b conjugate minus p conjugate. But because conjugate is reflecting across a real axis, and reflecting across a real axis doesn't change lengths at all, this means that this is actually true, and bp equals bp prime. So hence p equals b plus c plus minus bcp prime, and d is a midpoint of pp prime. So if we have that, and if we take the average, we end up getting this. So the foot of the altitude is 1/2 times the sum of the coordinates minus the product of these two times the conjugate of p. So now that's that, now we have all the theory out of the way, we can start solving the IMO problem. So here's the IMO problem. Let ABCD be a cyclic quadrilateral. Let P, Q, and R be the feet of the altitudes from from D to the lines BC, CA, and AB. So this should be P. So this should be P and this should be Q instead. And we want to show that PQ, this length here, PQ is equal to QR. I should draw that in red, sorry. That PQ equals QR if and only if that strange condition here, this very weird condition. Hopefully we can reduce this strange condition into something else. So let's find out under what conditions are PQ equals QR. Well, if you look closer at the diagram, you might notice that PQ and R might be collinear. Actually, this is a direct result from Simpson lines, if you recall my video on that. So now we know this. So what makes this problem very suitable for complex numbers? Well, we have all of these points on a circle, and we have feet of the altitudes, so might as well just set this circumcircle to be the unit circle. So I'll just go ahead and let that be O. Hold on just a second. So there's the origin O. And this is the unit circle. So now we're going to list out what we know. So A equals A, B equals B, C equals C, D equals D. Then we have that P is equal to 1/2 times A plus C plus D minus ACD conjugate from what we discussed earlier. And then we have that Q is equal to, oh wait, this should be BC, sorry. So B plus C plus, and then minus BCD conjugate. And then 1/2 times C plus A plus D minus CAD conjugate. And then R is equal to 1/2 times A plus B plus D minus ABD conjugate. And what we want to show is that the point P, that PQ is equal to 2 times PR, or something like that. So, or we want to show that P minus Q is the same as Q, has the same magnitude as Q minus R. So if we end up subtracting P and Q, we end up getting P minus Q is equal to 1/2 times, then the C's cancel out and so do the D's. So we get B minus A plus CAD conjugate minus CBD conjugate. And then Q minus R is equal to 1/2 times, then the A's cancel out, so do the D's, so we get C minus B plus a BAD conjugate minus CAD conjugate. And we can actually factor both expressions. So we have 1/2 times, this is B minus A, and then this is a minus C times D conjugate times B minus A. And this is 1/2 times C minus B minus AD conjugate times C minus B. Then after further factorization, we get that this is 1/2 times B minus A times 1 minus CD conjugate, and then this is 1/2 times C minus B times 1 minus AD conjugate. And now we want to find out under what conditions are the magnitudes of these equal. Because we have the 1/2 in both, we can just erase that. And we want to find out, and this is 2 times it, so times 2 times 2, so 2 times it, 2 times, and then times 2. So we got rid of the 2 in front. And we want to find out when the magnitudes are equal. So B minus A times 1 minus CD conjugate is equal to C minus B times 1 minus AD conjugate. And then here, we can now take out the B minus A and C minus D. So B minus A times 1 minus CD conjugate is equal to C minus B times 1 minus AD conjugate. Now what? How can we get this D conjugate out of the expression? Well, now we recall that D conjugate is equal to 1 over D because D lies on the unit circle. So we end up getting B minus A times 1 minus C over D is equal to C minus B times 1 minus A over D. Then if we multiply both sides by the magnitude of D, which equals 1 by the way, this ends up being B minus A times D minus C is equal to B minus C times D minus A. And in terms of length, this is just equal to AB times CD is equal to BC times DA. So this is the grand condition that we have. This is the condition that we want to prove is equal to the angle bisector condition. So now we return to our initial diagram here. We've gotten rid of the points P, Q, and R entirely, so we can get rid of all of those. And then we have A, B, and C. We have the angle bisector, and then we have a point D, and then we have this angle bisector here. And suppose that we want to prove that the angle bisector concurrent condition is equivalent to AB times CD is equal to BC times DA. So let's prove that the angle bisector condition implies that AB times CD equals BC times DA. Suppose they intersect at a point K. Then how can we relate them to ratios? Well, this should remind you of the angle bisector theorem, which states that AB over BC is equal to AK over AC, which also equals AD over DC. So if we erase this guy in the middle, then we can cross multiply and get what we need. So now assume that AB times BC is equal to BC times DA. Then if we have the point here, K is the foot of the angle bisector from ABC onto AC, then AB over BC is equal to AK over KC. So that means that we know that DA over DC is equal to AK over KC. And because the angle bisector theorem has a corresponding converse, that means that DK bisects angle ADC. And therefore, we have the equivalence. So angle bisector condition is equivalent to AB times CD is equal to BC times DA. And with complex numbers, we show that this is equivalent to PQ is equal to QR. And we are done. We solved the 2003 IMO problem number 4. The main tool we use to solve this problem is complex numbers. We use complex numbers to show that PQ equals QR is equivalent to AB times CD is equal to BC times DA. And using this, we use an angle bisector theorem to finish the problem. So thank you so much for watching. I hope you